Okay, so yesterday we started, I introduced matrix multiplication, so how to multiply two matrices and get a new matrix. And so at this point in our development of matrix algebra, we've introduced addition and subtraction and multiplication. We also had scalar multiplication, which is like a special thing for matrices. But we don't have one other operation that we'd have for numbers, which is division. So we need to figure out how to sort of divide by a matrix. And things are a little tricky here, maybe trickier than multiplication even. And so I want to motivate this a little bit just by going back and talking about division for numbers and sort of maybe cast that in a slightly different light than what we are usually used to here. So let's just, by example, let's just go back to numbers and let's divide, I don't know, let's divide by 2. Yeah. So you guys know how to divide by 2. Let's say I wanted to do like, I don't know, 8 divided by 2. Okay. So we all know this is 4. That's fine. I'm not interested in that though. What I'm interested in is what are we doing when I do this? And what am I really doing when I divide by 2? And there's maybe a bunch of ways that I could answer that question. But here's one way that is going to be helpful for us to understand matrix division. Matrix division is dividing by 2 is the exact same thing as multiplying by 1/2. So this is the same thing as 8 times 1/2. Okay. So I don't know. One way to see this is to remember how multiplication of fractions works. If I have 2 fractions, I just multiply the numerators and the denominators straight across. So I would think of 8 as 8 over 1 times 1/2, and then I just multiply 8 times 1 is 8, and 1 times 2 is 2. And so this, multiplying by a fraction is the same thing as dividing by that number, right? Okay. So we don't always think about division in this way, but it's going to be helpful for us in a second with matrix division. And this thing here, this 1 over 2, is another way of writing this. This 2 to the negative 1, which maybe we would call the reciprocal, right? So I'm sure you guys have all heard the word reciprocal. If I have a number, I just flip it under. So the reciprocal of 2 is 1 over 2. So dividing by 2 is the same thing as multiplying by the reciprocal. And in general, dividing by a number is the same as multiplying by the reciprocal. Okay. So dividing by a number is the exact same thing as just multiplying by its reciprocal. The only number that doesn't have a reciprocal is 0, because I can't divide by 0. So I can't multiply by 0's reciprocal. It just doesn't have one. That's undefined. Okay. So the idea that we're going to try and capture for matrices is this idea of reciprocal. In some sense, I'm going to tell you about the reciprocal of a matrix. But we're not going to use the word reciprocal. Instead, we're going to use this, we're going to use this word inverse instead. For numbers, we call it reciprocal for some reason. For matrices, we're going to call it inverse for some other reason. I'm not going to convince you that these are good names, but these are the names that we use. So, right. I guess maybe a little bit is, maybe I should really call this the multiplicative inverse, meaning that it sort of undoes multiplication, sort of the opposite of multiplication. So since multiplying by this is the same as dividing, and dividing is sort of the opposite of multiplication. Anyway, we want to capture this idea with matrices. So let me tell you about the inverse of a matrix. That's what we're going to find here. And by this logic, we can sort of divide by a matrix by multiplying by the inverse of a matrix. But there's going to be some caveats here. So here's a definition for us. Suppose A is a matrix. And I'm going to write this for now, an n by n matrix, but we're going to come back and fix this because it's not quite right. For now, it's just, it has some dimension m and n. Then the inverse of A which I'm always going to denote as a to the -1, just like for the reciprocals of a number. So a to the -1 is the inverse of a, is a matrix so that the following things are true. A times A inverse, so multiplying these two matrices, will give me the identity matrix. Give me the identity matrix. So remember I talked about the identity matrix yesterday. This is a square matrix, and it looks kind of like this. It has ones down its diagonal, and it has zeros everywhere else, right? That was this I, this guy here, just to remind you. So ones down the diagonal and zeros everywhere else. And this was taking the role of the number 1 for us for a matrix. So multiplying by the identity didn't change anything. This is, if I take A times I get I back. So the inverse is defined by saying if I take A times its inverse, I should get the identity. There's one more condition, which just says that if I do this in the other order, A inverse A, I should still get the identity. So if I multiply them in either order, I get the identity. I mentioned this yesterday, that in general, order matters when you multiply matrices. So A times B, if A and B are matrices, A times B is not the same as B times A in general. So I need both of these conditions to make this work, because in general, there's no reason that these should be the same. But I'm going to say that if they are the same, you're the inverse. So I have to have these two conditions. Okay. So A times A inverse is I, and A inverse times A is also I. This is just like with reciprocals in numbers, because if I take a number x, so here's a little aside for you. If I take a number x and I multiply by its reciprocal, 1 over x, what do I get? Well, that's going to be that's going to be x divided by x. Well, anything divided by itself is 1. So really, this same property holds for numbers too. It works the other way if I flip them. And so I'm really capturing this property here for inverse of a matrix. It's sort of saying A divided by itself, A divided by itself is the identity matrix, which is kind of like our number 1. Okay. So this is our abstract definition of what an inverse is. It's a matrix that satisfies these two properties. And I just want to notice now, I said A was an n by n matrix. But let's maybe pause for a second and ask, does that make sense? And maybe I just need to erase the board. Give myself some room. So far, A is m by n. Okay, so I have I equals A inverse, let's say. Okay, well, if A is m by n, then what do I know about the dimensions of A inverse for this even to make sense, for this multiplication to even make sense? Well, all I know is that the number of rows of A inverse has to be the same as the number of columns of A. So this has to have n rows. So its dimension is n by something at least. I know this. Okay. But I know the opposite thing is also true. So again, A is n by n. And here's n by something. And what happens here? I need this dimension, the number of columns, to be the same as the number of rows. So this has to be m. Okay. Now, in general, what we're going to say is the following. Hang on one second. I want to make sure. Right. Okay. So this would have to be sort of the dimension of A inverse is sort of flipped, right? A was n by n. A inverse is n by m. Well, let's remember one other thing is that how big is this guy? And what is the result of multiplying these guys? Well, this is a square matrix. I is a square matrix. And its dimension is going to depend on what the dimension of this product is. How do I know the dimension of a product? Well, I take just the outside guys when I line them up like this, right? These guys match, so the multiplication is defined. And to get the dimension of the whole thing, I just take the outside guys. So here I see I has to be m by m. Oh, but if I come down here and do the same analysis, Now I'm taking the outside guys. Oh, that's n. So this is actually an n by n. So I is at the same time an m by m and an n by n. So the only way this makes any sense is if m equals n. Yeah. So m has to equal n. And so A can't just be any matrix. A has to be a square matrix. A is a square matrix. Which just means that A is n, maybe n by n. It has the same number of rows as it does columns. Okay. So let me just summarize what we just did here, in case that was fast or confusing or anything. Let's just summarize this in a nice, neat statement, which says the following. Here's our fact. The only matrices which can have inverses are square matrices. So the only way a matrix can have an inverse is if it has the same number of rows as it does columns. If those are different numbers, there's no inverse. Okay. And one other fact is that if A has an inverse, well, I'll put it this way. Oh yeah, if A has an inverse, it only has one. So maybe I'll say it is unique. So there's only one inverse of a matrix, is the point. If it has an inverse, it's only going to have one inverse. It won't have like 5 inverses. It'll just have one. Yeah. So these are our facts that make sure everything here works. So if your matrix is square, it might have an inverse. If it's not square, there's no inverse. You don't have to waste your time. And if you have an inverse, there's only one inverse. So just compare this, for an instance, with reciprocals, maybe in numbers. The only number that doesn't have a reciprocal is 0. But I can find lots and lots of matrices already that don't have inverses, aka don't have reciprocals, because there's plenty of matrices that aren't squares. Just take any 2 by 3 or 4 by 6 or whatever. Wherever the number of rows is different from the number of columns, you won't have an inverse. That's a whole lot of matrices. So our situation is different already from the situation of numbers, but that's okay. We can still do a lot of stuff. So when finding inverses, we only care about square matrices. Okay. Cool. So I've given you an idea of just what just a definition of what inverse is and what kind of matrices are even relevant for discussing inverses. It turns out it's only going to be square matrices.
And a square matrix would be like 2 by 2, 3 by 3, 4 by 4.
Yes, absolutely. Yep. Anything where the number of rows is the same as the number of columns. So, yep, 2 by 2, 3 by 3, 4 by 4, and so on. Those are all square. Anything else will not have an inverse automatically. Any other questions? This is a good place maybe to pause and ask. So of course the question now that I've told you about this thing is, how do I find one, right? If I give you a square matrix, how do I find its inverse? And here's another question.